Well, we're now looking at section 2 in chapter 17, which discusses buffers. Now, buffers are solutions of basically a weak conjugate acid base pair. So you kind of have the combination of both together. And they're particularly resistant to pH changes, even when strong acids or bases are added. And your blood is a really good example of like a natural buffer. And your blood can undergo a variety of like inputs while keeping the pH consistently in the same range, basically maintaining a healthy, a healthy system. So how a buffer works. So let's say we have a buffer here with equal concentrations of hydrofluoric acid, which is a weak acid, and its conjugate base, so F minus, dissolved in solution. And let's say we add a small amount of hydroxide to the solution, so we're adding a strong base to this. And what ends up happening is that the OH minus will react with the HF to make more F minus in solution. But the overall change will be minimal in regards to the overall pH. And same thing if we have a buffer solution, same buffer solution, but we add like a strong acid to it, a bunch of extra hydrogen into it, and you end up getting more HF. So it kind of shifts one way or the other. Now, when we go to calculate or kind of understand what we're getting when we have it, you have your weak acid. Okay, so you're going to have your Ka. For your generic weak acid situation. And if we rearrange this equation, we end up getting Ka equals H3O plus times A minus, or the concentration of the conjugate base over the concentration of the conjugate, or the acid. So taking the negative log of both sides, we get the negative log of Ka equal to the negative log of H3O plus the negative log of A minus over HA. And you've got pKa there, you've got pH there, and then you've got a relationship relating the conjugate base and the acid in this event. All right, so basically pKa is equal to pH minus the negative log of the base over the acid. Rearrange this a bit, okay? So we move things around so that we get the get rid of the negative sign, things like that. So pH is equal to pKa plus the log of base of the concentration of the base over the acid. So this is the Henderson-hasselbach equation. And so let's say we want to know the pH of a buffer that is made up of 0.12 molar lactic acid, which is the weak acid, and 0.10 molar of 0.10 molar sodium lactate. Okay, or the Ka for lactic acid is 1.4 times 10 to the negative fourth. So we've got some initial concentrations. We have initial concentration of the weak acid, and we have the initial concentration of the salt and a conjugate base. So you have a 0.1 for the base and a 0.12 for the acid, and take the Ka value, which was given, and then just solve. So your pH is 3.77. The pH range is the range of pH values over which a buffer system works effectively. So if you add, obviously if you're going to add, a ton of base into it, you'll eventually exceed the ability of the buffer to kind of hold back the change in the pH, and eventually it'll swing pretty far in the pH. But you have a kind of a point, and it's related to where basically the pKa value is. Gives you an idea of the pH. So if you want a specific buffered solution, you might look at a pK or a Ka table to identify an appropriate weak acid that would kind of fit within the pH range of a buffered solution that you're looking for. So when strong acids or bases are added to a buffer, it is safe to assume that all the strong acid or base is consumed in the reaction. So we assume that the strong acid goes in and interacts with the conjugate base. And if we put in a strong base, it interacts with the weak acid completely. So there's nothing left kind of beyond that. So the key in that is that we'll take the strong acid approach. So you've got this buffer containing HX and X minus. You add a strong acid, and then you get HX plus H2O, right? And then we recalculate the concentrations of HX and X minus, and we use Ka to calculate the pH, the new pH. And we're going to do an example problem here. So we've got, let's say, so first, determine how the neutralization reaction affects the amount of the weak acid and its conjugate base in solution. So you have 0.3 molar of each. You add 0.020 moles of sodium hydroxide. So that is going to decrease the acid and increase the conjugate base. Okay, and so you would just change your values and then plug it into the equation to find the new pH. And then use the henderson-hasselbach equation to determine the new pH of the solution. All right, so here's an example. A buffer is made by adding, well, this was, well, this is actually what was described in that previous graphic. But so you've got 0.3 moles of each one of these in 1 liter. So you've got 0.3 molar solutions of each of these. So those are your concentrations, and you know the pH to start with is 4.74. You want to calculate the pH of this solution after 0.020 moles of NaOH is added. So before the reaction, they're equal, and so therefore pKa is equal to the pH, so therefore 4.74. Now, if we add 0.02 moles of sodium hydroxide, then you're going to see a change in the acid and the conjugate base. So we now have these new concentrations, and you're just going to plug those in to the Henderson-Hasselbach equation and calculate the new pH. All right, and that is where we're going to stop for today, and I will see you in class.